PLS, right? But if our model is not exploratory in nature, then we should not be actually using PLS. So it's our job as researchers to be ethical enough and to mention that in our research papers that the model which we are testing or the relationships which we are testing, that is exploratory in nature. And that's the reason why we are going ahead with PLS. Again, PLS, because I'm going to just address your question. So because we are using PLS and we are using PLS to test exploratory models, a lot of assumptions are actually relaxed when we are using PLS. For example, the assumption of normality is relaxed when we are using PLS, right? The assumption of not having any missing data, again, is relaxed when we are using PLS. We can actually have much smaller data sets when we are using PLS to analyze our models, again, because the entire model which we are testing, that is exploratory in nature. So we do not have, or a lot of research doesn't exist with respect to that particular thing which we are testing, or those relationships which we are testing. And on a lot of respondents we might not get when we are collecting data on such newer topics. And as a result of which, PLS gives you those advantages where a lot of assumptions are relaxed. But again, it should be only used in specific scenarios where we are testing an exploratory model. Because CB-based or covariance-based structural equation modeling doesn't relax any of those criteria, as a result of which we see that anytime our model doesn't fit any of those criteria, it will give us an error. Coming back to the question of negative error, why do we get negative errors? It can again happen because of multiple reasons, like we can have missing data, we can have outliers in the data, we can have data which might be displaying univariate normality but might not have multivariate normality. So all these assumptions have to be met, and only then we can proceed with analysis of our data with the help of CB-based SEM. Right. So now, why are we using, again, coming back to structural equation modeling here, when we are collecting data using structural equation modeling, we are firstly collecting data with the help of observed variables. We collect data on several questions, which again can be, in other words, called as observed variables or items. We are collecting data on observed variables, and we are trying to find out, we can try to find out the relationship between different observed variables with the help of a path analysis. If you want to model your observed variables into unobserved variables, which is the latent construct, you can also model your variables in that particular manner, and you can find out the relationship between the different unobserved variables. Also, while analyzing or while going through the entire methodology of structural equation modeling, we not only analyze relationship between two different variables to identify the relationship of one variable, or the two similar types of variables like observed with observed or unobserved with unobserved. We can also try to find out the relationship between observed variables and unobserved variables, which we usually do with the help of a CFA model, right? Confirmatory factor analysis model. So there, when we are using a confirmatory factor analysis model, we simply try to find out whether the observed variables have any relationship with the unobserved variables, or in which manner they actually are related to the unobserved variables. So a lot of things can be actually tested with the help of structural equation modeling. Now, this is how a structural equation model would look, or a data which has been modeled into a specified model would look like this. Now, this data again, this model can again be looked at into two different parts. Firstly, we have this part where we see that there are these four boxes or four rectangles which you can see. These are the four variables on which we have collected data, and this is an unobserved variable on which we have not collected data, but we simply have an assumption that these all four observed variables on which we have collected data are simply reflections of this particular unobserved variable. So we are modeling it in such a manner, and when we simply analyze only this part, or just if we simply ignore any relationship between the latent constructs, that simply becomes the analysis part, which is covered with the help of confirmatory factor analysis. But once we start analyzing relationships between the different unobserved variables or the latent constructs, which simply are those PPT, please. Yeah. Yeah.
More light on direction of arrows.
Yes, direction of arrows. I'm going to come to that. Once I start discussing the individual part, I'll come to that. So when we are, if we simply ignore, if we are simply ignoring these regression relationships, right, between, but once we are analyzing only the relationship between observed variables and unobserved variables, that simply is the part where we are talking about confirmatory factor analysis. So when we are analyzing a structural equation model, the analysis firstly starts by firstly checking the different assumptions of structural equation modeling, and then we can start with our analysis on CFA. It would be more suitable to say that we should firstly go ahead with an exploratory factor analysis, establish the variables which are loading into one construct, and then we can come to this part where we can model our variables accordingly, or we can specify our models accordingly. Now, all these different signs do have a different meaning. We are going to come to that, right? Right. Now, as I was discussing what all we can do with the help of structural equation modeling and what we cannot do with structural equation modeling, we can definitely talk about plausible relationships which might exist in the real world when we are testing relationships or testing hypotheses with the help of structural equation modeling. We can definitely talk about what type of relationships might exist in the real world, plausible relationships, but we cannot directly comment on the causality part, right? That can only be achieved with the help of experiments. Okay, now, when we come to the basic logic of SEM, so here, every theory model implies a set of correlations and why variables are correlated. Now, the theory is valid when we can find out the observed variances, the hypothesized variances and covariances in the modeled data. We can only identify, we can only check for those variances which we have hypothesized, those covariances which we have hypothesized, and once we find out that those same patterns of variances and covariances also exist in our model, then we can actually say that our model is actually a good fit with the data which we have, or whether it's not a good fit with the data which we have, right? Now, when we are collecting data, obviously, we will have, when we are collecting data, we will obviously have data which has different types of patterns within inside, right, within that particular data. Now, whatever model we have made or whatever model we have specified, that particular model might not satisfy or might not be in a position to justify each and every relationship between those variables, right? So we just need to find out to what extent the variances or covariances can be modeled, and the remaining things can be taken care as residuals, or can be seen as residuals. But yes, obviously, when we are forming a structural equation model, we are expecting that at least more than 50% of the variance in the data set should be explained by the model. That is ideally what we are expecting. Otherwise, if most of the variances exist in the residuals, then definitely we can actually think of a different model, or a better model which might actually help us identify all the relationships which we have hypothesized. So this is again a basic manner in which we are actually running structural equation modeling. We firstly build a knowledge base, we collect data, we firstly do a literature review, we identify hypothesis or relationship which exists in the literature, or which we can actually hypothesize certain relationships from our observations. Based on that, we form a hypothesis, we collect data to identify or to measure such variables. Then we design and run the model. Design simply means that we are specifying a model to test those hypotheses, and we are running the model to find out whether the model is a good fit with the data or not. Now, if the model is not a good fit with the data, one thing which we can do is we can reject the model outrightly, and we can just stop our analysis, and we can just we can think of a different model, or we can modify the model. If the data is not a good fit, we can use different modification indices to modify the model in a logical manner, and we can try to fit or try to see to what extent we can actually fit the existing data with the model. But yes, obviously, if it's a good fit, then we have tentative support for the theoretical model. Again, why it's tentative? Because definitely we cannot exactly talk, we can only talk about plausible relationships. Now, we have already talked about this. What are the different capabilities of structural equation modeling? We can definitely do path analysis, we can do confirmatory factor analysis, and we can also test the structural model. Right? Path analysis simply is the analysis where we are trying to find out the relationship between two observed variables, two or more than two observed variables. When it comes to confirmatory factor analysis, we are trying to find out the relationship between observed variables and unobserved variables. And when it comes to structural model, which again is the final stage of structural equation modeling, there we are simply trying to find out the relationship between two unobserved variables or two latent variables, right? Minimum two latent variables, it can be more than that. So these are the three things which we can actually do with the help of structural equation modeling. Now, coming to the different approaches, yeah.
Is it possible to do SEM only with the help of this SEM software?
Amos?
Yes.
No, we can do it with multiple softwares. You can use R to model to perform an
What's the meaning of confirmatory?
confirmatory. Okay, the actual meaning of confirmatory factor analysis. So, in order to understand the actual meaning of confirmatory factor analysis, we'll firstly have to understand what is an exploratory factor analysis. So,
My fear is many times just they apply just SEM software.
Okay.
It is confirmatory. But in actual sense, if you repeat the model multiple times, despite you are not using SEM, it is confirmatory.
no, no,
It is so.
no.
Confirmatory is never meant we are using only ML software, testing it. Confirmatory means we are testing the model multiple.
No. I do not. I do not. Sorry if there is any kind of a miscommunication. I do not mean when I say confirmatory factor analysis. I do not mean that confirmatory factor analysis is simply a factor analysis which is done on Amos. I definitely do not mean that. We can run a confirmatory factor analysis using various tools. One of those tools is Amos. Sorry.
Multiple times, multiple days.
No. We can run it. We can run the analysis once only, right? And we can say that we are doing a confirmatory factor analysis. What is actually a confirmatory factor analysis? Let's just firstly let me just firstly explain that, and then we are going to again come back to your question. So, in order to understand confirmatory factor analysis, we firstly have to understand what is an exploratory factor analysis. So we can use several tools to actually again go ahead with a exploratory factor analysis. The one of the very basic tools which you can again use would be an Excel, right? And you can definitely use IBM SPSS statistics to perform an exploratory factor analysis. Why do we do an exploratory factor analysis? We do an exploratory factor analysis to group observed variables which has some or which share similar correlations into one factor, right? We are trying to find out which are those observed variables which has a lot of similar correlations, which has a high correlation among themselves, and we simply want to converge them, or we simply want to combine them under one head with the help of one factor. That is the main objective of exploratory factor analysis. So we are exploring for factors. We do not know which are those variables which are going to get combined into a factor. So we are simply exploring the different variables, and we are trying to identify which are those variables which can get combined into a factor. When we come to confirmatory factor analysis, here the main difference between confirmatory factor analysis and exploratory factor analysis is that here when we come to confirmatory factor analysis, we definitely now know that which are those variables or which are those observed variables which would actually converge into one single factor. So we model it accordingly. We model all those observed variables into one factor, and we are now checking whether those four observed variables or five observed variables, whether they are actually loading on that one construct or not. So that's the basic difference. Now there is nothing where or there is no question of how many times we can actually run confirmatory factor analysis. Yes, you can run, if you have the same data, you can run confirmatory factor analysis multiple times. It's going to give you the same results, right? No, you do not.
So I started my exercise in 2007.
Yes.
So I was doing this mistake.
Which mistake?
So I was feeling confirmatory means applying SEM and getting model, it's okay.
No, confirmatory simply means that you are pre-specifying the relationships between observed and unobserved variables, and you are confirming whether this relationship exists or not.
So I was doing this mistake when I met with one of the very good researchers. You might have seen one book by Ajay Gaur and Sanjay Gaur.
Sorry, I'm not aware.
For SPSS using Ajay Gaur and Sanjay. Yes, very,
Yeah.
very good book. I purchased this book in 2005
Hmm.
from Delhi.
Hmm.
So luckily we delivered one lecture in Amritsar. One question was asked, what is structural equation modeling and what is confirmatory factor analysis?
Right.
He explained in detail that confirmatory means when you test a data, again you test the data, 3-4 times you can test and you find the same model is working, it is confirmatory factor analysis.
So if you are using the...
Irrespective of what software you are using, irrespective of the tool and technique you are using, that is confirmatory factor analysis. So what researchers are doing, so they are dividing their data in 3 parts.
Right, right,
So one is your pilot survey,
right,
then second is main survey can be divided in 2 parts.
right,
Right?
right,
So we can ask the same question from 2 different points,
right,
usefulness and important.
right,
So then we can test our model with 3 different type of data sets.
right.
Finally, you can combine. Then it becomes confirmatory factor.
Okay.
This mistake I was doing as
Yeah.
a PhD research scholar. He told me, he guided me
Okay.
how to correct it. Then I.
Okay, okay. Let me just now, given what you are saying, let me just give you an answer to that. So what you are saying, you are simply validating your model, right? You are validating your model with the help of multiple different data sets. As I was mentioning that if you're running the same data set multiple times, it gives you the same results, right? It doesn't give you a CFA result. Again, now, in addition to this, I would again mention that, for example, now let's say if you are not using SEM, right? If you are not using structural equation modeling. Again, structural equation modeling has 2 parts: confirmatory factor analysis, CFA model or measurement model in other words, and then we come to the structural model, right? Now, if we are not using a confirmatory factor analysis, if we are not testing the measurement model, where we are testing the relationship between observed variables and unobserved variables, if you are simply running an exploratory factor analysis with multiple data sets, it doesn't confirm your model. It doesn't confirm your model. An exploratory factor analysis is where an exploratory factor analysis is an exploratory factor analysis. A confirmatory factor analysis is a different methodology altogether, where we are simply confirming those structures, where we are confirming whether the observed variables, we specify a model, right? We say that a construct X has 4 different reflections or 4 different indicators which helps us in measuring that unobserved variable or latent variable, which is X. And those 4 observed variables could be X1, X2, X3, and X4, right? So this is the model which we specify. Now we put data into that model to firstly confirm, whether the data also shows that same pattern or not. That is confirmatory factor analysis. If you are using multiple data sets, right, you might be using multiple data sets for firstly doing. That's a very good way of running confirmatory factor analysis. You can actually collect, let's say, if you want to go ahead with a confirmatory factor analysis on any model, you can have a data set for which you are, with the help of which you are doing an exploratory factor analysis. Now, exploratory factor analysis with that data is telling you that these 4, X1, X2, and X3, X4, should combine into one factor. Now you're collecting data again, and now you are going to CFA. But CFA again remains the same thing. CFA is where you are testing the relationship between observed and unobserved variables. You're modeling it, you are predefining which observed variables are loading under which unobserved variables. So whenever you predefine such relationships, it simply becomes confirmatory factor analysis. By using multiple data sets, you are simply gaining more support for your results. That's it. But confirmatory factor analysis is simply the method where we specify a model, and then we try to find out whether the data is satisfying. Data again is satisfying the relationship between observed and unobserved variables. Right?
So basically, in structural equation modeling, what is the basic theme is, the construct, we call it latent construct, right? The word latent construct means that we are not exactly. So if I say, is someone happy or is someone satisfied? So we have 4 different items through which we are measuring that. And it's just through exploratory, what we do is we identify, are these 4 related to single construct? And confirmatory, we are bringing in and finding the relationship. You can have, I mean, Dr. Gore, what he must be trying to say, because a latent construct, that's why you need to be extra cautious. But conceptually, confirmatory factor analysis is confirming that these 4 converge to.
Very true.
So being
we
a
are
latent
focusing on both
construct,
the
you
options,
always should be
theory
careful.
building and theory testing.
Yeah, so as a
So
latent,
exploratory is for building your theory, and confirmatory is to test
yeah,
your
yeah.
theory.
So
For
conceptually,
example,
it's, yeah, concept,
circle model,
yeah.
it is confirmatory model nowadays.
Yeah, so conceptually it's the same,
fields.
only because a latent construct, that's why Dr. Gore must have said that you need to be extra careful with different data, right?
Okay. So now coming again back to structural equation modeling, what are the different types of models, or what are the different types of approaches which we can have while analyzing structural equation models? First is a strictly confirmatory approach. Strictly confirmatory approach simply tells us that we pre-specify a model. Obviously, we are specifying a model every time we are running analysis with the help of structural equation modeling. But when it comes to strictly confirmatory approach, we firstly pre-specify a model. We try to fit the data into that model. If the data doesn't gives us a good fit, we simply discard that particular model. So that's strictly confirmatory approach. Not many people would actually use a strictly confirmatory approach, because otherwise you collect a lot of data. It takes a lot of pain for us to collect a huge amount of data, and we cannot just simply discard the data because it doesn't fit a model. So we should definitely try to find out in which manner, or what are the different relationships which can actually be taken care of with this particular model. So a strictly confirmatory approach is, as the name suggests, is pretty strict, where it simply says that if the data doesn't fit the model, we are simply going to reject that particular data. The next approach is an alternating models, right? Is an alternating models approach, where we have multiple different alternative models. We specify different alternate models, and we try to find out or whether the data actually gives us a better fit in one of those alternate models. So that's an alternating models approach, where we are trying to find out which model or which specified model actually has the best fit with the data. So that's an alternating model approach. Again, a very commonly used model when we are testing, or when we are creating scales, when we are developing scales, we definitely go ahead with alternating models approach, where we are trying to find out different ways in which the constructs could be related. We formulate different hypotheses, and we try to specify multiple models, and we try to simply find out which model actually gives us a better fit. And based on that, we derive our conclusions. And the third approach is a model development approach. Model development approach, which again is the most commonly used approach which we see in today's time, where we firstly, again, pre-specify a model. Whenever I say pre-specify a model, it simply means we are mentioning our hypothesis, we are developing our hypothesis, and then based on those hypotheses, we are specifying a model. If the data fits the model, it's fine. If the data doesn't fit the model, we try to modify the model based on the recommendations which the data provides us, and based on that, we try to modify the model accordingly. Again, there are multiple ways in which we can modify the models. If there are issues with respect to normality, we can address normality issues. Univariate normality issues, we can address multivariate normality issues. We can also see if there are modification indices which are higher between two observed variables. We can definitely model covariances between two observed variables in structural equation modeling, which again is not possible when it comes to regression models, right? So we can find out whether two different observed variables has high correlation, and if that is the case, because of which, and if you have not modeled it, right, then definitely the fit will be poor, right? Whatever we model, whatever we specify as a model on our screen, we are simply trying to fit the data with that particular model. If we have not specified a relationship, while drawing that particular model or while specifying that model, obviously the data is not going to account for that particular relationship in that model, and as a result of which the fit would be poor. So if we can acknowledge those relationships, those high covariances or variances in the model, and with the help of modification indices, we can actually do that. And if we start if we start specifying those things in the model, we can actually get a very good fitting model, right? So most of the times, with the help of the model development approach, we arrive at a final model which gives us a good to moderate fit. So these are the three different approaches towards structural equation modeling. Now, when it comes to structural equation modeling, we have, again, to just elaborate on the different nomenclature which we use. We have observed variables. Observed variables are also known as items, right? These are simply those variables on which you are collecting data. Then we have unobserved variables, which are the latent constructs. Now, latent constructs could be of two types here. Observed variables also can be of two types. It could be endogenous, it could be exogenous. Endogenous is simply the dependent variable, a different nomenclature being used for dependent variable, and exogenous is simply a different nomenclature being used for the independent variables. So these are the different nomenclatures which you would usually see when it comes to structural equation modeling. Yeah.
So I would like to add one point here.
Yeah.
When we are modifying model,
Yes.
it is based on your modification index.
Right.
So MI first thing you can see, if it is negative, will not consider that part.
Sorry.
If the value is negative, you will not consider that part. If value is positive, majority of the cases we will select the value that will give us maximum positive value change.
Right. Right.
The second is we can test for the outliers.
Right. Outliers, usually we check it beforehand only. We check for outliers before coming to the stage.
It's an important step to modify or to develop your model.
Right.
So many times it happens that your fit indices very good, but RMR is not up to the mark.
Right.
The price scale is not up to the mark.
Right.
So in these type of situations, you can take help of your modifying modification index MI.
Right.
It can help us to identify or discover the question mark.
Definitely. So again, when it comes to the different fit indices, chi-square is something which we are not very much worried about, because
Only we usually focus on level of significance.
right. Only we again, many a times level of significance,
yes,
or for
yes.
most of the models, you won't find that, or you will always find that the p-value is less than 0.05.
Yes,
Right. Which simply means that the data doesn't fit the model. Right. So in such scenarios, again, why we do not worry much about chi-square is because chi-square is very sensitive to the sample size. So if you keep on increasing the sample size, the chi-square value will get inflated, and as a result of which, you will always get significant results, which is p less than 0.05. So for chi-square values, we do not worry much about it, but we definitely look at chi-square by degrees of freedom as the preferred index, right? And it should
That
be
should be
ideally
less than equal to 5.
it should be less than equal to 5. Some would say, again, there are various authors who have various takes. Again, some have a very strict take on Seaman by degrees of freedom. Some have a more relaxed take on Seaman by degrees of freedom. So there are different thresholds which do exist in the literature. Some would say that it should be less than 3. Some would say it should be less than 5 for large data sets. So Seaman by degrees of freedom definitely is a metric, or index which we should be definitely taking care of. Again, RMR, again, because of its nature,
0.8.
it should be, we try to keep it as low as possible because it's simply residual. So we try to keep it as less as possible. And with the help of these modification indices, we can actually take those values well within the limits. But again, there are certain things which we should always keep in mind, that just because modification indices are suggesting us something, we should not blatantly use modification indices and start specifying things in the model which doesn't exist, only if it seems logical with our model. For example, if there are two constructs in the model, two independent constructs in the model, and let us assume that both the independent constructs have 4 observed variables, right? Now, if modification indices suggest us that observed variable of one construct is having a high correlation with
Yes, yes,
observed variable of
spurious correlation.
right. No, the correlation exists, but we cannot actually model it.
Yeah, we
Right?
can
It's actually an issue because ideally we want all the different constructs in the model to be distinct from one another. So it's definitely an issue where the right way of addressing that would be to remove one of those observed variables, because two observed variables which are highly correlated should not exist in two different constructs, right? It should definitely not exist within that particular same model also. So in such scenarios, we should definitely be cautious about what can be done and what cannot be done. And then we should take care of, or we should modify our model with the help of those modification indices.
So in that case, exploratory analysis is the answer to the question.
Sorry?
If same factor or variable is loading in more than one
Same
yeah,
variable is loading on
more than one, we can delete that.
we can delete one of those. We can delete one of those variables. Okay, so we have already discussed about these things. So these are the commonly used symbols which we see in structural equation modeling. We take the help of circles or ellipses to define latent variables or unobserved variables. We can also call it factors. You can also call it constructs. There are various nomenclatures for the same thing. For observed variables, we use squares or rectangles to model such observed variables in the model. So that is the model. So when I was showing you a graphical representation of how a structural equation model would look, so there you saw a lot of different types of shapes and sizes being mentioned, right? So they simply mean these things, that an ellipse is a construct, a rectangle is an observed variable, a one-directional arrow is simply defining a regression relationship from one construct to another construct, or from one observed variable to another observed variable, or maybe from one unobserved variable to an observed variable. So whenever there's a unidirectional arrow, it simply refers to a regression relationship. And when we have arrows in both the direction, it simply talks about
So
a covariance.
in case of one direction arrow, majority of the researchers, they find difficulty in assuming which one is dependent variable and which one is independent.
Right.
They change the sign if model is not fitting and get the model fitted and produce results.
Okay,
So I've seen many papers. So they are doing this mistake.
so again, when it नहीं, recursive not so yeah. Yeah, so definitely it's not the right way of proceeding with a analysis on structural equation modeling, where you can actually say that X has a relationship with Y and Y also has a relationship with X. Structural equation modeling doesn't allow for such type of models, which is simply known as non-recursive models. Structural equation modeling doesn't allow for non-recursive models. We should definitely pre-specify our hypothesis, and based on that, we should definitely draw arrows from one construct to the other construct. And we have to be ethical enough to say that, okay, this is what we hypothesize, these are the results. Whether it's significant, not significant, doesn't matter. This is what we are getting, right? Yeah.
Oh, so good afternoon. I have one doubt.
Yeah.
Structural equation modeling is a correlational approach, right?
Sorry?
It's a correlational approach.
It's a covariance based approach.
Yeah.
Covariance based approach.
But it's not causal, right?
It's not causal. It's not causal.
Because in one of your slides, in earlier slides, when you're talking about the alternate approaches,
Right.
there you mentioned about causal models. I mean, you compare different causal models.
We compare different specified models. Causal models, obviously, we are simply. I should not be saying this as we are specifying causal models. We are simply specifying a relationship between multiple constructs or defining relationship between multiple constructs with the help of different arrows being drawn from one construct to the other construct. And similarly, again, as so I was mentioning that you can actually have different hypotheses and you might be willing to test which hypothesis gives you the best results.
Yeah,
So
yeah,
in
I
such
got
a scenario, you should definitely specify that you are going ahead with an alternating models approach. And that's the reason why you're testing for different models.
Okay. It was just mentioned like causal models, so I got
Oh,
confused.
no, definitely
In the
not.
slide, it was written like
Oh,
that.
okay.
So,
We do not test for causality
Yeah,
here. We are
yeah,
simply
yeah, that's right.
trying to test for plausible relationships which exist in the real world.
And one more thing,
Yeah.
I mean, we do the measurement model before doing the structural model, right?
Right.
We establish the measurement model, but many a times there is a challenge, like we have to do a trade-off between measurement model and structural model. Like if we remove a certain item, let's say the measurement model is getting improved, like the C mean by DF is getting under like 1.8 or so, and even the RMR and SRMR, these all are under check. But if we remove something, then the measured model is getting improved. But if we run the same in the structural model, then it is not, I mean, we are not getting the desired result. So, I mean, a case might come that a little inferior measurement model might give us more.
Are you
stronger
saying that the
structural model.
the model fit is getting impacted when you are going when you are model fit is getting impacted once you are going from measurement model? If let's assume that
No, not the measurement model. In the structural model,
Yes,
I'm talking
yes.
about the p-values, with the
no,
relationships.
yeah, definitely, yeah.
So how should we look at this trade-off? I mean, should we even be bothered, or I mean, I understand as a true scholar will always say that establish the measurement model first and then go to the structural model,
Right.
because that is how it makes sense. But in reality, when we do research, we are always driven by the greed or something like that to get better results. So where should we actually be
So I
focusing?
think you have already given answer to your question. You should definitely give up the greed on getting more number of significant results. We are not looking for significant results or insignificant results. We do not. That's not our aim. We simply are trying to fit the model with our data. If the data is if the data is fitting our model, if we are like you were saying, like for example, if I am simply removing certain observed variables from our model, right? And after that, I'm getting a measurement model which is having a very good fit. Now, ideally, when I go to the structural model stage, the fit should not be impacted to a very huge extent.
The fit is not impacted.
Fit would almost remain the same, right? Because those are the same constructs being modeled in the similar manner. So fit would definitely not get impacted. The only thing which you might see is that in some cases, some of the relationships might come as significant, and in other cases, some other relationships might become insignificant when either you add something or when you remove something. Now, the reason is very simple here. When you are adding any observed variables or unobserved variables into the model, that the other constructs in the model or the other observed variables in the model, they simply start interacting with that added variable. And as a result of which, you get a scenario where in a real world scenario, when all these 5 factors are into play, then in that case, what is going to be the significance of these relationships? That is what you are trying to test, right? Now, obviously, if you remove one variable completely from that model, you're simply eliminating that scenario from the real world scenario, right? And as a result of which, you get a different set of results. So obviously, you should never be worried about how many number of significant results you are getting in your research. While you're running your structural model. The main thing here is that once you have run your structural model, and let's say out of 5 relationships, you are getting 3 as not significant, 2 as significant. The decision on whether your paper would actually land in a good journal or would not land in a good journal simply will be decided by whether or by whether you can actually explain the reason behind those non-significant relationships. Most of the times what happens is when we get some non-significant relationships, we simply ignore those relationships, right? But if you give equal attention to those non-significant relationships, if you can discuss those non-significant relationships, talk about the plausible causes of those relationships becoming non-significant, then I think the paper still remains a strong paper.
My point was actually like, should we give more effort to, let's say, all the
No, definitely not.
no, in case of model fit indices in the Mason model, everything is under the threshold.
Right.
So we are good to go. So shall we focus? I mean, spend any effort on further improving the model, or we should leave it once it crosses the threshold?
No, if it is within the threshold, like if your model fit is fine, then you should not give any more efforts on making the model much better, because your non-significant relationships are still going to remain non-significant. Only the model fit is going to get better if you are still taking the help of modification indices. So it doesn't matter whether you try to make the model better or not. It's not going to help you in any manner that the non-significant relationships are going to become significant. So that's not going to happen.
Okay, many thanks.
Yeah. Now, when it comes to structural equation modeling, there are 4 different types of validity which we usually check: convergent validity, discriminant validity, phase validity, and nomological validity. Again, some of these validities are very specific to specific type of methodologies. When we are using specific type of methodologies, for example, nomological validity, you would mostly see in papers or in researches where a scale is being developed. So they are simply trying to find out whatever scale they are developing in order to measure a specific phenomena, whether it also justifies the existing relationships or not. So those are certain validities which are very specific to specific methodologies. But mostly you would see convergent validity and discriminant validity as well as phase validity being used in most of the research papers. Starting with phase validity simply tries to find out whether the questions which you have put in your questionnaire, whether those questions are making sense to the to the respondents or not, whether the respondents are able to respond to those questions without any ambiguity, whether the questions also measure the construct which it intends to. All those things are being checked at this level of phase validity. So how do we do it? We simply can make a questionnaire, the questionnaire which we want to float to the respondents. We can simply make a questionnaire, and we can make a 3-point scale. At one end, we can have not at all representative, and on other end, we can have completely representative of the phenomena, and we can just give those questionnaires to few experts, like 3 or 4 experts, some industry practitioners, and some researchers, and they will simply try to find out whether those questions which you are asking in order to, let's say, measure a specific phenomena like satisfaction, whether those questions actually does measure satisfaction or not. So that is what they are going to mention. If you are getting if for all the questions you are getting completely representative of the scenario, then you can keep those questions. For any questions where you're getting not at all representative or neutral, you can actually eliminate those questions from the research. So that is how phase validity can be checked. Convergent validity simply talks about whether the different observed variables which we are specifying in the model as loading on one construct, whether they do actually have a lot of correlation, a lot of covariances. Otherwise, we cannot model them into one construct. So convergent validity simply talks about that, whether the observed variables converge into one factor or not. And that again can be checked with the help of multiple indicators, like average variance extracted is one of the best indicator to find out convergent validity. We can also look at other matrices, like we can look at factor loadings. If all the factor loadings are above 0.6 or 0.7 ideally, then it says that convergent validity does exist for those variables which are loading on that particular construct. And the AVE value, which is average variance extracted, which you can directly get by squaring and adding all the standardized factor loadings. You can also find out whether the AVE, average variance extracted, is above 50% or is above 0.5 or not. If it is above 0.5, then we can say that convergent validity does exist. The other validity is discriminant validity, where we are simply checking the assumption that whatever constructs we do have in the model, whatever constructs we have in our model, they are actually distinct from one another, right? Like we were discussing that if we are having multiple constructs and those constructs have certain items which are correlating with each other, then that's not an ideal scenario. We do not want such type of a scenario, because ideally all the constructs which we have in our model, they should be distinct from one another. That simply increases the total variance which can be explained with that model. Otherwise, we will have a lot of shared variances, and the number and the amount of unique variance which can be explained by that model simply reduces. So discriminant validity is again one measure which we are testing when we are going ahead with structural equation modeling. Right? Let me just quickly go to that part where I can just talk about structural equation modeling and what is actually what are those structural equations. So this is a model where you can actually see a structural model. But if you take the left part, or if you take the right part only, or if you just simply remove the regression arrow from between zeta and eta, then in that case, you simply end up having the CFA model. Now, again, the CFA model is simply trying to establish relationship between observed variables and unobserved variables, right? So that is what we are trying to check. Now, when we talk about structural equation modeling, what are those structural equations which we are actually talking about? So in this model, we can see that there are two constructs. One is an independent construct, another is a dependent construct, right? The independent construct is being measured with the help of three observed variables, x1, x2, and x3. The dependent variable is being measured with the help of y1 and y2. And then we have delta 1, delta 2, and delta 3, which are simply the error terms or measurement errors, right? Now, if you want to know what are the different factor loadings, standardized factor loadings, the standardized factor loadings, again, which is very similar to beta values, which we usually see in regression results, right? The standardized coefficients. Here again, we have standardized coefficients, which are lambda 1, lambda 2, and lambda 3, which you can see in this particular model. So what are the different structural models which we actually see? If we simply take only two constructs and the different observed variables which are measuring these constructs, we can see that these are the different structural models. How do we get it? So you can just focus on any one of the relationships. So here you can see x1, which is the dependent variable, is equals to lambda 1 into zeta 1 plus delta 1. So that is the structural equation which we are actually talking about, right? These are the different structural equations which we are talking about. And we can actually write down the four different structural equations which are specified in this particular model one by one. And if you want to specify it in a matrix form, you can also show it in the form of a matrix by mentioning x equals to lambda x zeta plus delta. So that is how we can mention the different structural model. So this is just the matrix representation of that. The matrix model which I just showed you, that's just the elaboration of that particular matrix model. Now, if you want to now look into the entire, so we have been talking about the measurement model. If you now want to jump into the structural model, where we have now specified the relationship between constructs with the help of regression arrows. Now you can actually specify these relationships as well with the help of eta equals to standardized regression coefficient into eta plus tau into zeta plus xi. So that is how you can actually mention the entire structural model, or you can actually specify the entire structural model with the help of that particular equation. Right? So these are the different, in this particular model, here we have different measurement models, and we have this one structural model which we have specified separately. Now, once you have measured, once you have specified your measurement model, once you have specified your structural model, the final things comes to understanding the fitness of those models. And the fitness of those models can again be estimated with the help of various fit indices. We do not take the help of one fit indices because just to eliminate any chances of one fit indices being biased to certain parameters. So we take the help of multiple fit indices to finally conclude whether the data is a good fit, or whether it's a moderate fit, or whether it's a bad fit or a poor fit. So we take the help of various fit indices to actually conclude whether the data fits the model or not. So the first fit index which you would always look at will be the chi-square fit index. Unfortunately, chi-square fit index is extremely sensitive to the sample size, and as a result of which most of the times you might find out that the chi-square value is getting inflated when you are dealing with larger data sets. And also the chi-square value will come as significant, which simply means, again, the null hypothesis of chi-square relationship is that data fits the model. If the chi-square value is coming as significant, it simply means, which is simply p less than 0.05, it simply means that the data doesn't fit the model. So chi-square value, when you are getting it significant, there's no point of worrying, because that might happen because of larger sample sizes. We can simply jump into the other fit indices, which can give us a complete overall picture of the entire model. The other fit indices could be GFI, or you can look at chi-square by C-min by degrees of freedom, chi-square by degrees of freedom. The threshold values will be less than 0.03. Sorry, the C-min by degrees of freedom, the threshold value should be, ideally we should see a value which should be less than 3. Sometimes we can also take values which is less than 5 in case we are handling data sets which has a lot of data points. We also try to find out various residual estimating indices. For example, root mean square error of approximation. It's one of the fit indices it's actually an index which tries to understand the amount of residuals which we have in the model. Ideally, when it comes to residuals or any index which deals with residuals, we want values closer to 0. In this case, the threshold value should be less than 0.05, or we can go for moderately fit models, we can go to values up to 0.08. Same thing with RMR and SRMR. We want values which should be less than 0.05, or ideally we want values which should be less than 0.08. At the max, we can go till 0.08. Other fit indices, which are again in today's time very important, and you would see multiple times these indices being taken care of by multiple research papers, is NFI, RFI, IFI, TLI. So these are all incremental fit indices, non-fit indices, right? Tucker-Lewis fit indices, based on the different names of researchers who have given these indices. We have different fit indices, and whenever we talk about fit indices, we always want fit indices to be having a value which is very close to 1. Ideally, in such scenarios, we want values greater than 0.9, then only we can say that the model is a good fit, right? So these are all the fit indices which we would check. These are the threshold values, right? So this is where we've come to an end to this topic of structural equation modeling. If you have any questions, we will be happy to take those questions. Any questions?
So any good book for this?
I would recommend only one book, that is of Barbara Bryan. Yeah, that's one book which I can recommend. Yeah, Amos with R, Amos with, structural equation modeling with Amos, structural equation modeling with R. There are multiple books which has come now.
So if there are no questions, thank you very much. And we hope that you enjoy this next session. I'll hand it over to Professor.
Okay, thank you.
Oh, it doesn't work. Okay. So we'll break for tea, and we are going to meet around 4:45. 4:10 or 4:15 around this time. Okay. Yeah. Thank you. So tea is served outside, right? Yeah. Thank you.